When you read a sentence, you read it in order, word by word. But large language models don't work that way. They ingest an entire block of text all at once, as a simultaneous, unordered mass. This creates a mathematical hurdle known as permutation invariance. Permutation invariance means that changing the order of the inputs doesn't change how the system processes them. The model essentially sees a bag of words rather than a sequence. To see this flaw in action, look at this animation. If you feed an unencoded transformer the sequence ABC, and then feed it the exact reverse, CBA, the underlying math spits out the exact same geometric representation. To the bear model, the cat sat on the mat and the mat sat on the cat are perfectly identical. Without a mechanical way to tag the sequence of these inputs, the model is blind to time. It cannot grasp logic, track narrative flow, or cause and effect. In 2017, the original transformer architecture introduced a fix: sinusoidal position encoding. This method forced the model to rely on intersecting sine and cosine waves to stamp every single word with a distinct, fixed mathematical coordinate. Engineers soon shifted to an even more direct approach called learned absolute encoding, which powered early versions of GPT. Instead of calculating waves, the AI simply memorized a rigid dictionary of positions, assigning a static number to slot 1, slot 2, and so on. But these rigid coordinates hit a hard wall called the extrapolation problem. Extrapolation refers to a model's ability to handle sequences longer than what it saw during training. If a model was trained to memorize exactly 512 positions, feeding it a 513th word causes the math to break down entirely. Relying strictly on absolute coordinates limits memory. You cannot ask an algorithm to read entire books or scan massive code bases if it physically forgets how to count past page 2. Researchers solved this limitation by changing the reference point. When parsing language, the exact absolute page number of a word matters far less than its relative distance to the words around it. This brings us to ROPE, or Rotary Position Embedding. It physically rotates data vectors representing concepts based on their sequence position. When comparing words, absolute coordinates cancel out entirely. All that remains is the pure, fixed angle between vectors, preserving relative distance. Other architectures bypass coordinates entirely. Decay-based methods like ALiBi simply apply a mathematical penalty to weaken the connection between words as the physical distance between them increases. By encoding relative distance instead of memorizing fixed points, these methods allowed models to dynamically adapt to varying sequence lengths without catastrophic failures. Today, users demand models that can process tens of thousands of words at once. Retraining an AI from scratch to handle these massive inputs costs millions of dollars in computing power. To bypass that cost, engineers developed position interpolation. Massive texts exceeding training boundaries are linearly compressed like an accordion. But linear compression blurs nearby words, so techniques like yarn dynamically scale frequencies, compressing distant data tightly while preserving high-resolution spacing for local patterns. These scaling tricks require zero new learned parameters, enabling a model trained on just a few pages of text to instantly map and summarize a 100-page PDF. The physical world is not a one-dimensional sequence of words. Artificial intelligence must navigate variable image resolutions, two-dimensional layouts, and three-dimensional environments. Look at this matrix layout. Engineers are conquering spatial awareness using multi-dimensional rope and conditional position encodings. Instead of a single position coordinate, each data node gets independent rotational frequencies for height, width, and time. By running calculations across multiple axes simultaneously, models natively map the complex spatial layout of a photograph and track the exact chronological flow of moving objects in a video. Implicit relative position encodings started as a method to help algorithms sort text sequences. Today, it forms the architectural foundation, allowing artificial intelligence to map and ingest the entire physical world.